Let's look at the Simpson approximation for an integral that we computed with the trapezoidal approximation. If you recall, we had the integral from 1 to 2 of x times the cube root of x to the fifth plus 2x squared minus 1, a rather unfortunate integral that requires some approximation techniques or some mystical reasoning in order to get an antiderivative for that. So what we want to do is to compute the fourth order Simpson approximation. That is, we have an interval of length 1 and we want 4 subdivisions. So the subinterval length will be 1/4. So we have the same partition that we had for the trapezoidal rule. Basically, the problem is very similar. It just gives you an opportunity to practice the mechanism one more time. So we have the same partition: 1, 5/4, 6/4, 7/4, 2, and of course our function. Now the only difference here is, and they're subtle actually, when you think about the trapezoidal approximation and the Simpson approximation, the coefficient here changes, and then of course instead of all of these coefficients here being 2's, we have a 4, 2, 4. So there are some subtle differences between the Simpson approximation and the trapezoidal. So what we want to do is just go ahead and substitute, but just remember 1, 4, 2, 4, 1. That's the coefficient sequence for the Simpson approximation, and of course the 4 subdivisions works well because 4 being an even number. So now we do our approximation. We have the length of the subinterval divided by 3 times the number of subdivisions, so that gives us a 1/12. And then we see some similar computations from the trapezoidal rule. We get f of 1 to be 2 of 1/3, or 2 to the 1/3 power, and then the f of 2 is 2 times the cube root of 39. So that's the same, those two terms are the same as we computed for the trapezoidal approximation. And now we'll see a lot of similarities here. So now we have the 4 times the x, and then of course we raise the 5/4 to the 5th power, 2 times 5/4 to the 2nd power, minus 1, all raised to the 1/3 power. And then we move to this term, we have the 2, and I went ahead and reduced the 6/4 to 3/2, so we get 3 to the 5th times 2 to the 5th plus 2 times 3 squared divided by 2 squared minus 1 raised to the 1/3 power. And then for this term, of course, we have 4 times 7/4, and then of course 7/4 raised to the 5th power times 2 plus 2 times 7/4 raised to the 2nd power minus 1 all to the 1/3 power. So again, these should look very similar, the only difference being in the coefficients here. And so what I did in this next line is I just reduced the numbers a little bit for ease of calculator use. I use the Google calculator, it's simple to use. So we have our 1/12, and here pretty much no change except to absorb the 2 into the 16 to get an 8. And here, of course, the 2's absorbed to give us a 3, and just wrote 3 to the 5th and 32, and then, of course, 9/2, the 2 absorbing into the 4 to give us a 2. And then here it did the same thing. The 4's absorbed, that leaves us with a 7, and then this is the same, and then, of course, the 2 absorbs into the 16 to give us an 8, 49/8 minus 1, quantity to the 1/3 power. So now at this point, like I said before, I used the Google calculator and I rounded out to several decimal places, and then your text asks for 6, so we just round here the 6 up to 7, so we have 3.571557, which is an improvement over the trapezoidal rule. So basically what I want you to understand, again, this is just a lot of arithmetic, it's a lot of busy work, but the theory supports the definition of the Riemann integral, and we see that no matter how unfortunate looking, we can always get a handle on definite integrals. The elegance of the fundamental theorem of calculus is something we enjoy, but it requires us to find the antiderivative, that is the big F. And when that's not something that's available to us in a way that we can actually realize, then we are fortunate to have approximation methods for definite integrals. And we are done.